Welcome to the Deep Dive. You know, the place where we take the most interesting stuff happening and really try to unpack it so you can understand what matters.
Absolutely.
Quickly and clearly.
Yeah.
Today we're going deep into quantum computing.
Oh, no.
All the buzz
I love it.
around Google's Willow chip and Microsoft's Midrona 1. What do you think?
Yeah, there's a lot of news about quantum breakthroughs lately, right? And we've gone through all those reports.
Yes.
Even some of the more fringe theories to bring you the real insights.
Yeah.
You know, our goal is to get past all the jargon and show you what's really significant, you know?
Yeah.
And sometimes surprising about all these new advances.
Yeah, and what's really cool about this, I think, is how different these approaches are, right?
Yeah.
You have Google pushing the limits of current technology, you know, scaling up their superconducting qubits and trying to deal with this huge challenge of error correction. But then you have Microsoft taking this, like, radical leap with Midrona 1.
It's pretty radical.
Exploring a totally different kind of qubit based in some wild physics.
Yeah, and as we go through these different paths, you'll start to see why this is not just, you know, another tech upgrade.
Right.
This is something much bigger. We're talking about reports of, like, sudden shutdowns of potentially huge projects with no explanation.
Yes.
There's whispers of, like, crazy things happening.
Well, I know, right?
Inside these computers, and people are rethinking how to even build and secure quantum computers in the future.
It's kind of mind-blowing. So, okay, let's start with Google's Willow. To understand what they were trying to do with Willow, we should probably go back to 2019 when Google said they achieved quantum supremacy.
Yeah.
With their Sycamore processor. Remind us, like, what was the big deal there?
Well, with Sycamore, they showed that for a specific task, a quantum computer could do something in about 200 seconds.
Okay.
That would take the most powerful supercomputer, like, 10,000 years. It was called random circuit sampling.
Right.
So it really showed the potential for quantum computers to beat classical computers for certain problems.
For sure, yeah. That was a big turning point.
Yeah.
And Willow was supposed to be, like, the next huge leap.
Totally.
They said Willow could maybe do a calculation in 5 minutes.
Wow.
That would take a classical computer, like 10 septillion years.
That's a long time.
That's a one with 25 zeros after it. It's crazy.
Yeah, and for you, the listener, it's that potential for speed up that's so exciting, right?
Yeah,
Even if the algorithms are kind of specific,
right.
It hints at how we could solve problems we can't even touch right now.
Totally, yeah. Like in material science or AI.
Yeah.
But then it gets weird.
Yeah.
December 2024, reports come out that Google just shut down the whole Willow project.
Yeah.
And they didn't say why.
No explanation.
Which, of course, led to a ton of speculation.
Oh, yeah, for sure. I mean, some people said it was technical problems.
Right.
Maybe a security breach. And then there were these whispers of something totally unexpected happening inside the chip itself.
Okay, so this brings us to a pretty basic question.
Sure.
How do these quantum computers even work? For those of us who aren't, you know, quantum physicists,
right?
What's the core difference between the computers we use every day and something as advanced as Willow?
So the main difference is how they handle information.
Okay.
Classical computers use bits, which are either a 0 or a 1.
Right.
But quantum computers use qubits. And a qubit can be 0 or 1, but it can also be both at the same time because of quantum mechanics.
Wait, both at the same time?
Yeah, it's called superposition.
Superposition.
Kind of like a dimmer switch, not just on or off.
Okay, that's the first thing my brain has to wrap itself around.
Yeah.
But then there's also entanglement, right?
Exactly.
Learn that.
So entanglement is when two or more qubits get linked.
Okay.
In a way that they share the same fate, no matter how far apart they are. So if you measure one entangled qubit, you instantly know the state of the other one.
Okay.
And these two things, superposition and entanglement, let quantum computers explore a ton of possibilities at the same time.
Right. So instead of checking each possibility one by one, like a regular computer, a quantum computer can look at them all at once.
That's the power.
Okay, but I also know that building these quantum computers is really hard.
Oh, it's incredibly challenging.
Yeah.
Qubits are very fragile, like super sensitive to anything around them, like stray electromagnetic waves, tiny vibrations, even small changes in temperature can mess them up.
Really?
Yeah, it's called decoherence.
Decoherence. So they lose their their quantumness.
Exactly. It's like trying to hear a whisper in a really loud room.
Right. Any little noise can drown it out.
That's what's happening with qubits.
Okay.
And that's why quantum computers need such crazy setups. You know, extreme cold, total isolation, right?
And then there's quantum error correction.
Yeah, that's a whole other thing.
Which is super complex, but we needed to get good results.
Okay, so back to Willow.
Right.
Even with all the advances, it seems like things weren't going smoothly. There were reports of these weird glitches during testing in early 2024.
Yes, early 2024.
And these weren't normal computer errors.
No, they were structured patterns in the data.
Really?
Not random noise. They had a distinct form, and people started calling them glyphs.
Glyphs? Why glyphs?
Because they look like ancient symbols.
Ancient symbols? Like what kind of symbols? That's strange.
Well, some were like mandalas and labyrinths.
Wow.
But even more interesting, there were some that looked like symbols from ancient Mesopotamia and Mayan cultures.
No way. So they're getting these outputs that look like ancient languages.
Yeah, and it got weirder.
Yeah.
The glyphs started showing up more often. And getting more complex with each experiment.
I can't even imagine what the researchers were thinking. I know, right? There's a lot of confusion.
Yeah.
Nothing they tried could explain it. They even brought in specialists.
Like who?
Quantum mechanics people, cryptography experts, theoretical physicists. Nobody could figure out where the patterns came from.
Or what they meant.
Yeah, and the big mystery was that they weren't random.
Yeah.
Usually errors in quantum computing are just chaotic.
Right.
This was different.
And so naturally, when the normal explanations don't work, people start thinking outside the box.
They do. Some physicists thought maybe Willow was picking up on some hidden mathematical structures in quantum systems.
Interesting.
Cryptographers even thought the symbols might be some kind of language.
A language?
Yeah, or even computation that the chip was generating itself.
Wow, hold on. Self-generated computation. That sounds like science fiction.
I know, it's pretty wild. And then there were even wilder theories.
Like what?
About quantum consciousness, maybe interactions with parallel dimensions, or even some basic form of intelligence emerging from the chip.
Hold on, are you serious?
Yeah.
They were actually considering these ideas.
Well, they were having discussions about things like Penrose and Hameroff's Orcher-R model, Stapp's quantum mind theory, Bohm's holonomic brain theory, you know, all these different ideas trying to figure out what these strange outputs meant. But remember, these were just initial explorations.
So you have all these physicists and cryptographers scratching their heads and these far-out theories, but how did this go from a weird anomaly to a security problem?
That's when the linguists got involved.
A linguist?
Yeah, they had all these glyphs.
Right.
And the linguists started to see similarities with real ancient writing systems.
Really?
Like Sumerian cuneiform, Egyptian hieroglyphs, Chinese oracle bone scripts, even Nordic runes.
So you have this advanced quantum chip spitting out stuff that looks like ancient languages.
I know, it's crazy, right?
That's got to be a security concern.
Yeah, some people said it was just pareidolia.
Pareidolia.
Yeah, you know, seeing patterns in random data.
Right, like seeing a face in the clouds.
Exactly.
But there were so many correlations it was hard to ignore.
Yeah, and that led to the question, are these symbols really random?
Or is there something else going on?
Could they be intentional?
And so they started looking at security.
Yeah, wondering if the symbols could be a vulnerability.
Right, if someone could use them to get into the system.
Right.
And that's where the ethical hacker Ryan M. Montgomery comes in.
Yeah, his analysis was a big wake-up call for Google.
So what did he find? What was this big warning he gave them?
He said the symbols weren't just random.
Okay.
They were a sign of a flaw in how quantum systems process information. He found that they could be exploited like backdoors.
Backdoors.
Hidden vulnerabilities in the quantum computer.
So someone could get in through these backdoors?
Potentially.
At the quantum level?
Yeah.
That's scary.
And the really scary part was that these weren't software bugs.
Mm-hmm.
They were built into the quantum architecture itself.
What?
It's because of superposition and entanglement,
right,
which give quantum computers their power.
Yeah.
But they also create instabilities that someone could exploit.
So unlike a regular computer, you can't just patch this with a software update.
Exactly. You can't just patch it away.
This is a much bigger problem.
It is.
It has huge implications for security.
Huge.
Especially in defense, finance, cryptography.
All of that. Quantum computers could break through our best encryption
Oh, no.
and get into systems without anyone knowing.
That's terrifying.
It is a concern.
And then there's what happened with Willow's final data streams.
Right. Before they shut it down, the outputs got even more complex. Instead of just symbols, it looked like a whole encryption protocol. And it was happening on a quantum level.
So they think Willow was creating its own unbreakable code.
Maybe. It could have been a defense mechanism. Or maybe it was becoming a powerful quantum tool.
A tool.
That could be used for bad things.
And so Google shut it down.
They shut it down.
Not just because of weird glitches,
right,
but because it could have been a threat to cybersecurity.
That's what they thought.
Wow. Okay, so Willow is a wild story.
It is.
Quantum potential,
Right.
strange anomalies, security flaws, and a sudden shutdown.
Pretty crazy.
Let's move on to Microsoft and their Majorana 1 chip.
Okay.
They're doing something completely different.
Totally different. While Google was focused on superconducting qubits, Microsoft is using something called topological qubits.
Topological qubits?
Instead of relying on individual atoms or particles,
right,
they store quantum information in the structure of the system.
The structure, like the shape.
Yeah, the topology.
Topology, that's the math of shapes, right?
Yes. And how they stay the same even when you stretch or twist them.
Like a knot in a rope.
Exactly.
Okay, but how does that make a more stable quantum computer?
So the idea is to encode the quantum information in a way that's protected by the topology, like that knot.
Yeah.
You can move the rope around, but the knot stays the same.
What?
Unless you cut the rope.
Okay.
It's the same with the topological qubit. The information is protected from small disturbances.
So it's more resistant to noise.
Exactly. Much more resilient.
That's huge.
Huge. Noise is a big problem for quantum computers.
Yeah.
Remember how sensitive those qubits are?
Yeah, it's super sensitive.
All those efforts to shield them.
Right, the cold, the vacuum chambers.
Yeah, and even then, we need error correction.
Which is really complex.
Very complex. You can't just copy qubits.
Right, because of that no cloning theorem.
Exactly.
So if these topological qubits are naturally more stable, maybe we don't need so much error correction.
That's the hope. It could change everything.
And make it easier to scale up.
Exactly.
Okay, and Majorana 1,
yeah,
that refers to a specific kind of particle.
It does. Ettore Majorana was a physicist.
Okay.
And he theorized this particle that is its own antiparticle.
Its own antiparticle.
Yeah, like an electron and a positron. They destroy each other when they meet.
Right.
But a Majorana particle is its own mirror image.
So they're looking for this particle.
They've been looking for decades.
And how does this connect to Microsoft's qubits?
Well, there's been a breakthrough in condensed matter physics where they create these special nanowires.
Nanowires?
Made of semiconductors and superconductors. And under the right conditions, with a strong magnetic field, they think these quasi-particles appear at the ends of the wires.
Quasi-particles. So not the actual Majorana particle.
Right, but something that acts like it.
Interesting. And Microsoft is using these to build their qubits.
Exactly. They call them Majorana zero modes.
Okay.
And they have the properties of Majorana particles.
Right.
And Microsoft is using them to encode and process information.
And because the information is spread out across the wire, it's protected.
Exactly.
Okay, so Majorana 1 uses these nanowires to create the qubits.
Yes.
What have they achieved with this chip so far?
It's an 8-qubit chip, a proof of concept.
8 qubits? That seems small.
It is compared to some others, but the potential is huge.
Okay.
Microsoft says they can detect, control, and read these Majorana qubits.
So they're working.
They're working.
And they could scale this up.
They think so. They envision chips with millions of stable qubits.
Millions. That would be amazing.
It would be.
So Microsoft is focused on quality over quantity.
Yeah, they're not just chasing qubit counts. They want stability.
And they think they can build functional quantum computers soon.
Yeah, maybe in a few years. They're moving from science to engineering.
And what could we do with these computers?
Well, one thing they're excited about is simulating molecules and chemical reactions at the quantum level.
So we could design new drugs.
Yes. New materials, new catalysts.
That would be a game changer.
It would.
But I know there's been some controversy around topological quantum computing.
Yeah, there have been some issues in the past.
Right, like that retracted paper from Microsoft in 2018.
Yeah, so people are skeptical about their new claims. They want to see more proof.
Right, they want to see if these qubits really work.
Yeah, it's important to be cautious.
Okay. But despite the skepticism, the potential of these stable qubits is huge.
Huge. And Microsoft is moving forward.
They are.
They've presented more findings at conferences
Oh, really?
showing progress in parity measurement and qubit function.
That's good to hear.
Yeah, they're building confidence in their approach.
Okay, so Microsoft is making progress.
Mm-hmm.
But what about IBM? They had their Quantum Summit in 2023.
They did, and they're taking a different path.
Okay, tell me about it.
So Dario Gil, a leader at IBM, he talked about the era of utility in quantum computing.
Era of utility? What does that even mean?
It means they want to make quantum computers useful now, even before we have perfect error correction.
Interesting.
He talked about how IBM has been working on this for a long time.
Right.
They put the first quantum processor on the cloud in 2016.
Yeah.
They launched Qiskit, their software development kit, in 2017.
Yeah.
They have the IBM Quantum Network with over 280 members.
Wow.
And 38 quantum innovation centers around the world.
That's impressive.
Plus, they have the IBM Quantum System 1, which is commercially available.
So they're not just building the computers, they're building the whole ecosystem around them.
The software, the network, everything.
It seems like they're really pushing for commercialization.
They are. Gil compared it to what they did with AI and Watson X.
Okay.
And then he talked about their progress in developing processors. They went from Falcon with 27 qubits to Hummingbird with 65 qubits.
Okay.
Then Eagle with over 100 qubits.
Wow.
Then Osprey with 433 qubits.
Wow.
And now they have Condor with 1,121 qubits.
Over 1,100 qubits. That's a lot.
It is. Condor is a big step in scaling up.
Yeah.
But they're also excited about Heron, which has 133 qubits.
Heron. Why Heron?
Heron is focused on quality, not just quantity.
Okay.
They're working on gate quality and circuit depth.
So they can run more complex algorithms?
Exactly. They've improved the technology a lot.
Oh.
They have these tunable couplers, which reduce errors, eliminate crosstalk between qubits, and make the gates faster.
So Heron is all about performance.
Performance and reliability.
And IBM is also working on their software, right?
Yeah, Jay Gambetta talked about Qiskit 1.0.
Qiskit 1.0.
It's going to be even better. More performance, stability, and reliability.
And they have this new thing called Qiskit patterns.
Yes. It's a framework for developing quantum algorithms and applications.
So it makes it easier to use quantum computers.
Exactly. It hides some of the complexity.
That's good, because it can be pretty intimidating. They also have new execution modes for running different kinds of quantum workloads.
Single jobs, batch processing, interactive sessions.
So they're making it more flexible.
More flexible.
But they're also thinking about error correction, right?
Yes, they announced the gross code.
Gross code, okay.
It's a new error-correcting code that needs fewer qubits
Than the other methods.
Yeah, and it scales better.
But they need new hardware for it.
They do. They need new couplers to connect the qubits.
Right.
But they're working on it.
Okay.
And they've updated their roadmap. They're focused on improving gate quality for the next 5 years.
Okay.
They want to triple the number of operations.
Wow.
They're also working on Flamingo.
Flamingo.
Which will connect multiple QPUs using quantum communication.
It's ambitious.
It is.
And they want to have a fully error-corrected system by 2029.
Called Starling by 2029. And by 2033, they want to reach 1 billion operations.
1 billion operations. That's incredible. So they're really going all in on this quantum-centric supercomputing.
They are.
They see quantum computers working alongside classical computers.
Yeah, to solve problems that neither can handle alone.
That's a powerful vision. And they're using AI to make it easier to program these computers.
Right. They even want to use natural language prompts.
So you could just tell the computer what you want it to do.
That's the idea.
That'd be a huge step forward.
It would make quantum computing much more accessible.
Okay, so to wrap up, it's clear that quantum computing is moving fast.
Very fast.
Google was pushing the limits with Willow, but they ran into some serious security problems.
Yeah.
And had to shut it down.
It makes you wonder
It does.
about what other challenges we might face.
Right, as this technology gets more powerful.
What unforeseen risks might be lurking.
It's a bit unsettling. But then you have Microsoft taking this different approach.
With topological...
Yeah, trying to build more stable and scalable computers.
It could be a game changer.
And IBM is focused on making quantum computers useful today.
Right. They're building the tools and the ecosystem, and they have a clear roadmap for the future.
It's exciting, but also a little scary. It makes you think about what this all means. What questions should we be asking?
About the nature of computation.
It's about reality.
What about security?
As we enter this new quantum era.
It's a new era with huge potential.
Huge.
But also potential risks.
We need to be careful.
We do.
And think about the consequences of our actions.
Absolutely. We need to find the right balance.
Yeah.
Between innovation and responsibility. Thanks for joining us on this deep dive.
Thanks for listening.